Hello, everyone. My name's Manon, and I work with Joel Wertheim at the AVRC. And I'll be talking about some of our work on HIV transmission networks among transgender women in Los Angeles County. And the driving question behind this is whether we can use molecular analysis to understand the factors that perpetuate new infections among transgender women. Because we know that transgender women are at increased risk for HIV. So in the US, the prevalence of HIV among transgender women is around 22%. And alongside this, they have a low diagnosis rate compared to men who have sex with men, for example, who are another high-risk group. Their risk is multifactorial. There's a list on the side of the slides, but they are a community with socioeconomic disadvantage, high rates of alcohol and drug use, high rates of sex work. But as well as this, their risk is often not well captured by HIV surveillance. So in the data sets that we have from Los Angeles, they're sometimes, their risk group is categorized as men who have sex with men, sometimes as heterosexual, and there's also a proportion of them who inject drugs. And as far as we know, there are no published phylogenetic studies which try and resolve these routes of transmission using their genetic sequences. So a little background about the Los Angeles County epidemic. It's a vast city, and it also happens to be where the first ever cases of HIV were diagnosed in 1981. There's about 10 million people who live in Los Angeles County. There's 50,000 people with HIV, about 2,500 new cases per year. And since 2005, the poll sequences which are generated for drug resistance testing have been reported to public health. Public health has a database with all of these sequences from all of the diagnosed patients. So the database from 2016 contains over 22,000 unique individuals for whom we have a genetic sequence alongside demographic and clinical data. And we also know that in Los Angeles County, there are probably around 8,000 transgender women. So what we do in our lab is that we use HIV sequences to understand HIV transmission. So here we have two transmission chains, and we have the virus being transmitted from one individual to the next. And what we get is that we get these different viruses, virus genetic sequences, and what we want to know is who infected who in the population. So we reconstruct the relationships between those viruses using a program developed by Joel Wertheim called HIV Trace. So HIV Trace counts the number of differences between those viruses, and if they fall below a pre-decided threshold, they get linked together in the network. And so these evolutionary relationships between the viruses are used as proxies for relationships between individuals. However, as you can see on the top, for example, if three genetic sequences are very closely related to each other, we can't resolve the order of transmissions, and those individuals will all appear linked to each other in the network. Also, when we have linked viruses, we don't know if we might be missing an individual along that path of transmission. And these analyses of genetic sequences allow us to understand trends in transmission at the population level. So, for example, it can help us uncover hidden patterns of transmission. For example, on the left here, we have a little cluster, a little transmission network in which, where the nodes are colored by self-reported risk group. And so we have a self-reported heterosexual man whose genetic sequence clusters only with men who have sex with men. This is from the UK HIV drug resistance database. And we can conclude from this that there's probably a high chance that this man was infected through sex with men rather than heterosexual sex. On the right-hand side, we have a transmission network reconstructed from sequences from people who inject drugs in the UK, and the nodes are colored by origin, region within the UK. So the red nodes are from Scotland, injection drug users, and the yellow ones are from the rest of the UK. And in this case, we can see a huge cluster in blue of sequences, all from Scotland, all from injection drug users, and they're a circle because they have two drug-resistant mutations which are the same. And in this case, the network analysis allows us to identify this huge cluster of rapid transmission of HIV among a small group in Scotland. So the clustering method identifies a high-risk group with elevated transmission rate. So we took all the sequences from Los Angeles and we reconstructed a network, part of which is shown on the slide. The Los Angeles County epidemic is dominated by men who have sex with men. They represent nearly 70% of the cases. About 1/3 of the sequences clustered in the network. That means that for those individuals, at least one other individual in the database has a close genetic sequence. The transgender women, as I said, they can be put into the database as men who have sex with men, as heterosexuals, as people who inject drugs. So we decided to reclassify our transgender women as either having reported injection drug use, so PWID, people who inject drugs, or non-PWID, so sexual risk. And so in the network, there were 126 clusters comprising 167 transgender women. And this meant that 40% of the transgender women in the network were clustered. And so the subset of the network that's shown here is actually all of the clusters which contain at least one transgender woman. The first thing that we looked at was who was most likely to cluster in the network. And this is because clustering is a signal of potentially high transmission rate. So here we have the bar chart represents the proportion of that subpopulation who cluster, and the numbers across the top are the odds ratios for clustering in a univariate logistic regression model. So the population that clustered the most were actually transgender women reporting sexual infection, sexual transmission risk. And they were 2.5 times more likely to cluster than cis-female heterosexuals, who were the reference group. So they were actually even more likely to cluster than men who have sex with men. And we know that men who have sex with men cluster a lot, potentially because there are high transmission rates, but also because we have high sampling of men who have sex with men. They're more likely to be diagnosed earlier in infection, and therefore they're more likely to end up clustered in the network. However, with transgender women, we specifically know that they have low diagnosis rate. And so this increased rate of clustering really underlies an increased risk of transmission for that group. We used some network measures to look at where the transgender women fell within the networks, and one of these is assortativity. And assortativity measures the tendency for nodes that share an attribute to link together. So in the cartoon network on the slide, we have 2 transgender women, and they link to each other in that cluster. So the more times we would see that pattern in a network, the higher the assortativity of transgender women would be. And we can measure assortativity of a given trait, for example, transmission category, how assortative are individuals in the network by transmission category. But we can also break down that trait to look at the assortativity of one of the risk groups within the transmission category. So how assortative are transgender women compared to men who have sex with men? So this shows us the measure of assortativity for each of the risk groups compared to the null distribution, which is in gray. So men who have sex with men were most likely to link to other men who have sex with men, followed by heterosexuals. And then the third group most likely to link to other individuals of the same risk group were transgender women. So they were highly assortative, and it was highly significant. And in fact, we looked at the pattern of clustering of transgender women in the network and found that for an individual who is not transgender, if they cluster with one transgender woman, their probability of being linked to another transgender woman is 9 times higher than anyone else in the database as a whole. Next, we looked at mixing patterns within the network. So who else do transgender women link to? And broadly, what we find each time we have the observed measure compared to the null expectation, we found that transgender women were much more likely to link to other transgender women and to cis-male heterosexuals than they were to men who have sex with men, compared to the expected distribution. However, if you look at the raw numbers, so the expected number for linkage to men who have sex with men would be about 75%, given the number of men who have sex with men in the network. And we still observe nearly 60% of the links are with men who have sex with men. So the majority of links are still with men who have sex with men. However, that's much less than we expect. So in summary, transgender women are the subpopulation most likely to cluster in the network, indicating high transmission rates. Transgender women were more likely than expected to link to other transgender women and to cis-male heterosexuals. And transgender women were much less likely than expected to link to men who have sex with men. Linking to one transgender woman in the network increased one's odds of linking to another transgender woman 9-fold. And this highlights a potential new avenue for identifying at-risk transgender women who have not been tested or diagnosed, because you could use the network to select non-transgender women who link to at least one transgender woman for enhanced partner services. So at the moment in Los Angeles County, not everyone gets a partner services interview for them to name their sexual partners. But if you could ensure that anyone who's linked to at least one transgender woman gets the interview, potentially they could name other transgender women who either, are HIV infected and not diagnosed, and you could diagnose them, or if they're not HIV positive, then they could be linked to PrEP, and with the eventual aim of both increasing diagnosis rates among transgender women and decreasing infection rates. So with that, I'd like to thank Joel Wertheim in particular, but our collaborators at the Los Angeles County Department of Public Health as well. Thank you.
Hi, great presentation. I just wanted to ask if you had any treatment data, if these sequences are older, if you've seen any difference in the clustering since the more widespread advent of virologic suppression, and what the rates of suppression are in the transgender women population, if you have them.
We actually do have viral load data for a lot of the individuals in the population, but we haven't looked at them specifically in transgender women at all. Was there another part to your question? Oh, differences so the sequences, the oldest sequences are from basically most sequences are post-2008, so they're all quite recent. There are some changes over time, though, which are that both among cisgender and transgender people, there's a lot more clustering of people who inject drugs a long time ago than there is now, hopefully because kind of interventions in that group are a bit bigger, and we see that really strongly in the transgender women who inject drugs. There's loads of clustering for sequences early 2000s early 2010s, and not so much now.
I'm just curious how similar the viruses are within a cluster.
So the cutoff that we use is 1.5% genetic distance. So every individual within a cluster is a maximum of 1.5% genetic distance from another individual in that cluster. And the length of the genetic sequence that we're using is 1,300 bases. So only a few nucleotide substitutions away.
Any other questions? I have one for you. How do you generate the null distributions for expected assortativity and expected linkage between groups?
So we have, I have slides for that. So we have a static network in which we annotate every individual with risk group information. And we count then in the true network how many links we have between the transgender women and every other kind of risk group, which is counted on the left here. And then we randomly relabel all of the individuals in the network, keeping the structure of the network static, and recount each time the number of links between risk groups, and also re-estimate assortativity. And so that way we're able to generate the null distributions.
Great, thanks. And we have time for one more question.
Just a quick question. Do you think sampling density would affect your assortativity calculations? How deep the populations are sampled? How many cases you find within each one of the populations?
Yes, I think in general, clustering approaches are really affected by sampling. And you can only kind of start to think that it's not being affected when you have pretty good sampling of all of your populations, which, cumulatively over time, we have pretty good sampling for all of the populations. However, one of the subpopulations that we probably have least good sampling for is transgender women. So the fact that we, despite low sampling, still see high rates of clustering and high rates of assortativity, I think testifies to how strong the signal is in that population.
Thank you very much. It was a great
Thanks.
presentation.